All right, let's go ahead and continue. So we're still talking about balance forces. Remember, we may use the word balance. We might use the word equilibrium. Okay, they mean the same thing. What does that mean? That means that all the forces cancel each other out. What could happen is that object could be not moving, staying still, or number two, it could be moving, but moving at a constant pace in a straight line, never changing directions, never speeding up or slowing down. Okay, so let's go ahead and keep going here. Says here, example is fishing. So, what if you're out fishing and you've got your fishing pole in the water and you've got this bobber just floating right there above the water? Okay, the bobber's not moving. The moment that a fish comes to try to get that bobber, get the bait, okay, the fish starts to pull down, that bobber is going to go down. To keep this in equilibrium, you've got to pull back up to keep it in equilibrium. Eventually, one of you are going to win, right? You are the fish. So it says here an example of fishing. A fish pulls 10 newtons, and I just made up a number, down, and you pull 10 newtons up, and it's going to maintain an equilibrium. Okay, let's keep going. A car on cruise control. Well, how is this going to be in equilibrium? I've got air and friction from the road, right? Or friction pushing. Let's just pretend 100 newtons on the car, right? We've got the friction from the road. We've got air that's pushing against it on the car. But the car is pushing against the air and the friction from the road. A 100 newtons. And it will continue that, and it will go in a straight line until you push down on the brakes or you turn the wheel. But it would be in equilibrium for however long that can happen. Now, unbalanced forces is forces acting on objects that are not equal to zero. Man, I am having problems with my lines. Okay, comma, produces a motion in the direction of the greater force. Okay. It says here, draw a picture of something that's unbalanced force. Well, okay, let's go ahead and do that. So we're going to draw, I've got a bumpy gravel road here. Here is we've got a wagon. We've got a kid here that's pulling the wagon, right? And it's a little kid. So this kid is able to pull it 10 newtons, but the friction of this road, this bumpy gravel, is pulling 5 newtons. So can you imagine if this wasn't all friction, how much of this energy would be used to moving and pushing that object? Okay, so let's keep looking. Let's keep going. Page 2. It says here other types of forces. Okay, forces can do, now we know what can happen as a result. It can be balanced or unbalanced. But forces can act through direct contact or at a distance. All right. It says here, for an example, friction. Friction is going to be direct contact. Gravity. At a distance, there is no physical touching. That has to happen. Air resistance, direct contact. And when we talked about this in class last week, I gave another example, magnetism, right? At a distance, you can still feel the magnetic pull. Okay? So it says here, friction, the force between two objects in contact that resist the motion with each other. There's a couple of ways we can reduce friction. We can reduce friction by adding oil, water, ice. Okay? But even microscopically, no matter how smooth that object may be, or adding ice or freezing it, it still has what we call microscopic friction. Okay? There's always friction. So, we call that the coefficient of friction. It's a number that tells me how strong a frictional force will be for a particular weight. It says here, different surfaces have different coefficient of frictions. Okay? Ice has a lower coefficient of friction than sandpaper. Okay? Coefficient of friction has a unit. It is going to be, a symbol. We call that a mu. Values usually range between 0 to 1. These are not big numbers. Okay? Low coefficient of friction is going to be something that's very slippery, smooth. Very high coefficient of friction is something that's sticky, rough, like sandpaper. Okay, let's keep talking. There are, it says here, 2 types of friction for most surfaces. Okay, friction could be what we call static friction or what we call kinetic or sliding friction. Static friction is the resistance an object has to starting to move. Kind of like, imagine if you have a table and you have some objects on your table. You have a plate, you have a water bottle, a fork, and a couple other things on a table. Your table at home, your kitchen table. But if you were to stand at one end of the table and pick it up slowly, static friction would be the friction that's holding that plate, that fork, that water bottle, whatever, your cell phone, to the table. Okay? It's how hard and difficult it is. The resistance before it even moves. Eventually, you're going to pick it up and it's eventually going to slide off of that table. But for a while, static friction holds it there. Static friction is what holds your butt to the seat, so that way you don't slide off. Okay? When you put your water bottle or your cup on your table, static friction holds it there so it doesn't just slide on off. Kinetic friction is a friction experienced by a moving object. So static friction is the beginning friction that's holding it there. The kinetic friction now is once you get that object moving, then it's in kinetic friction. It says here, once motion begins, the frictional force decreases, and we can exert a smaller force on that object to keep the object moving at a constant. So have you ever had like a really heavy object and you had to push it or pull it? It took probably a lot of energy just to get it going. But the moment that you got it going and it was in the groove and it was moving, it didn't take the same amount of force or energy to keep it moving once it began moving. Okay? So the friction now starts to reduce once it's in kinetic friction or once it is in the process of moving. It says here the coefficient of friction is different for the static and the kinetic cases. So we call it mu little s, which is static, and the mu k is the coefficient of kinetic friction. That's how it's expressed or shown or written. It says here, you also might notice that it is often harder to get the object moving than to keep that object moving, right? Once it's going, it's got that momentum in it. Now it's moving, okay? But that static friction is really hard to try to sometimes to overcome, to get it to go. Gravity is a different type of force, right? It's a force that's at a distance that does not have to have physical contact. Gravity is the force of attraction between two objects. It says here, which one has more of a gravitational pull on the ocean tides on Earth? Okay, I'm sure you probably talked about that in middle school, but you should know that the moon actually has it has an influence on the tides here. Why the moon? Well, because it's closer. And so the closer, that should be an S. The closer objects are to each other, the more of a gravitational or attractional pull they have to each other. Okay? Kind of like, you ever been in the hallways, and I understand we haven't been in school hallways in quite some time, especially now, like when it used to be, when it was packed hallways. And you're walking down a hallway, and you're just walking and talking with your friend. And yeah, you're walking next to each other, but before you know it, you're not even paying attention. It's like y'all do bump into each other. It's that gravitational attraction pull to each other. And the closer you are walking with each other, the stronger that pull becomes. Okay? Everything that has mass, everything that is matter, has a gravitational pull towards it. Okay? And that will be the last equation we talk about. Air resistance is a direct contact type of force. Okay? A force placed on an object moving through the air, right? Let's turn the page, keep going with our notes. We're going to get into Newton's 3 laws of motion. Okay? Remember how I said, the story has it, Newton was sitting there under an apple tree, and an apple tree came and hit him down on the head. That's more like a rumor. Did Sir Isaac Newton sit often and look at things around him, the world, and think about things? Yeah, he did. Okay? But I think that was more of a rumor. That wasn't the true case. But he did notice that as things went up or as things fell down, okay, or released, they all kept on falling down towards Earth. There was some type of attractional pull towards the Earth because nothing or no one was falling off the planet, right? And when Sir Isaac Newton was around, they didn't have rockets and spaceships. So at that time, nothing would ever, get off of planet Earth. So his 3 laws of motion. The first law is also called the law of inertia. It states that an object at rest stays at rest, and an object in motion stays in motion. At a constant speed and in a straight line, unless acted upon by an outside force. And the majority of the time, that outside force is almost always friction here on Earth. Okay. It says inertia. Now, that word inertia has a definition. The word inertia is the tendency of an object at rest to stay at rest. Another way to say this is a shortcut would be resist change. Also, what we should write down here is if an object has more mass, comma, it has more inertia. Inertia is related to the amount of mass that object has. More mass, more inertia, meaning that the heavier it is, the harder it is to get that object to move, which makes sense, right? Going back to the static friction. Examples, it says dishes at rest. Too bad we're not in the classroom, so that way we can do that trick. I'm sure some of you have seen it before on TV where there's a table and it has a tablecloth on it, and there's the plate and a cup and dishes on it, and they yank that tablecloth as fast as they can, and the dishes don't even move. They stay at rest. Okay? They were the law of inertia, where they were not moving and they were not going to move. As long as you remove the tablecloth from under it, you were doing nothing with the dishes. They remained at rest and they just fell down towards the table. Another example would be, says here, bowling ball remains, let's say this, scratch that out, in motion until acted on by an outside force. That's a good example, though, because if you're to throw a bowling ball down a bowling alley, right, it's really oiled and greased up, really smooth and slick. That bowling ball, can you imagine if they were to make that even longer, that bowling alley that for you to, bowl? That bowling ball will continue to go in that straight line, if you're able to throw it straight, for forever until it hit an outside force. For us, when bowling, it would be the bowling pins would be the outside force. Okay? So that's a reason why almost always it's friction that slows down our objects, some type of friction. The next one, Newton's second law of motion, is actually our equation. It says here that the force of an object depends on the mass of that object and the amount of acceleration applied. Okay? Our equation comes out to F equals ma. It is on your formula chart. So the force equation equals mass times acceleration. This is the first time we take mass into account. We've used acceleration and we've never had force as part of our equation. So force and mass are two new ones. Okay, acceleration we're used to. Force does have SI units. The SI unit for force is a Newton or a capital N, not lowercase. And remember, I think I mentioned this before, but I'm going to say it again. Let me write it over here. Mass must always be in kilograms. Okay? Always. I'm going to put it right here. I don't care if we're talking about this equation or any other equation for the whole school year. In physics, when we talk about mass, it must be in kilograms. Now, if my mass is in pounds or grams or milligrams, I need to convert it. And yes, I said pounds. We would have to convert from the English system to the metric system, and we will learn that in the notes here. Okay? And we know that the SI unit for acceleration is meters per second square. So I'm just going to put acceleration meters per second square. Okay? So here's a couple of practice problems. Number one, how much force is needed to accelerate? So question mark F, that's what I'm looking for, is needed to accelerate a 1,300 kilogram, this is my mass, car at the rate of, this is my acceleration number. Again, how do I know what abbreviation goes where? Because I'm looking at the SI unit. Kilograms is mass, meters per second square is acceleration. I'm looking for force. My answer better be in a Newton. Okay? So let's go ahead and do that. F equals ma. Just like we've done before. This is our equation we're going to use. Am I able to use my equation? Yes, I have the mass. Yes, I have the acceleration. All I have to do is multiply those numbers and get my answer. Please make sure that when you do your notes, you show me all your work. Y'all are starting to lose points because you're just writing down the answer and you're watching my video and just slapping down the answer. No, show me the steps. The same thing for your homework. If you do not show me your work, you're not going to get credit. Some of you are wondering why you're making 50s on your homework because you're just writing the answers down. Lazy. So let's go ahead and do this one. 1,300 multiplied by 1.5 equals blank newtons. You can solve for that. Now, I do want to do this over here. That's my equation. F equals ma. Well, just in case, I'm going to, if you like to, you can always put this into the triangle. Cover up the equal part. Mass is being multiplied by acceleration, so they're going to go into the equation first. They have to be multiplied. And so they have to go down here at the bottom. What's left over? F for force. So if I need to, I can cover up acceleration. Acceleration equals force divided by mass. If I'm looking for mass, mass equals force divided by acceleration. Okay? The next one. A frog leaps from its resting position at the lake's bank into a lily pad. This is my v sub f, my initial velocity. If the frog has a mass of 0.5 kilograms, and that's going to be my m number, and the acceleration of the leap was 3 meters per second, what is the force, question mark F, that the frog exerts on this lake's bank when leaping? All right, well, F equals ma. Do I have the m? Yes. Do I have the a? Yes. They actually also gave me the initial velocity. They're trying to throw me off. Not only do I have what I need, but I do not need to change the variables at all. Okay, I'm going to leave it as is. I'm going to get the mass of 0.5, the acceleration of 3 equals blank newtons. You need to solve this or you will lose your points. Let's keep going. The next one here, we've got another question. Starting from rest. Oh, they did it again. Okay. VI is 0. At the center of a skating ring, 2 skaters push off of each other over a period of time, which is 1.2 seconds. Oh, they gave us more. They gave us T. What is the force, question mark, F, of the push by the smaller skater? Not only do we want to know the force, but we want to know the force of only the smaller skater. Well, who's the smaller skater? Here's the before and here's the after. That's person 1, person 2, person 1, person 2. Well, the smaller skater is going to be the 40 kilogram person because they have less of a mass than the 48. So this is the person that we're going to focus on. Okay? So we're looking only at the smaller skater. I'm going to go ahead and we're looking for force. F equals ma. Do I have the mass of the smaller skater? Yes, 40. Do I have the acceleration? What about that? Is that acceleration? No, it's not. And some of you, I would have got you on this one. This is not the acceleration. Look at that. That's the velocity. Not only is it velocity, but look at over here. This is my VI and this is my VF. What is the velocity here for my VI? 0 meters per second. And it told me from rest. What was the VF? They told me 3 meters per second. And they told me the amount of time that this acceleration had occurred was 1.2 seconds. This is actually a 2-step problem. We're going to come over here first. And we need to solve for acceleration. Acceleration equals final velocity minus initial velocity over t. If they didn't give us the VI, VF, and t, then yeah, I guess we could use one of the kinematic equations. Oh, that would be horrible. But yes, if need be, we can pull back A equals VF squared minus VI squared over 2 times D if needed. Okay, so like I said, what we've learned in the past units are not going to leave us. We continue to keep that information and carry it over to the next units. This is acceleration. Do I have the VF? Check. The VI? Check. The T? Check. I have everything in the correct order. Plug it in, find the acceleration, and then plug it in over here so that way you can find the force of the smaller skater. So let's do that. 3 take away 0 over 1.2. Right? Take away 0 is not going to do anything. That's going to be blank meters per second square. Now, that's not my answer, but that is going to help me to get my answer. We're going to get that number and bring it over here. The mass of the smaller skater is 40. The acceleration of the smaller skater you found over here. You plugged it in. Please be prepared for a question like this on the quiz or test. Okay? What if the smaller skater was in pounds? Then that means that you would need to convert pounds to kilograms, and then you would need to find the acceleration and then solve for the force. That could happen also. Okay? You're going to get that number, plug it in over here. You're going to get your answer in blank newtons. Okay? Let's keep going. Newton's third law of motion states that for every action, there is an equal and opposite reaction. And I give a few examples, right? If you ask somebody, "Oh, what happened to your hand? What happened to your knuckles?" and they tell you, "Oh, because I got so mad I punched the wall." Doesn't make sense, dummy. You're not very smart because obviously the wall punched you back. And when people are like, "What do you mean the wall punched you back?" Obviously the wall got a good hit on you if you're walking around with broken knuckles, right? So that's proof that for every action, there's an equal and opposite reaction. Now, don't get me wrong. If you barely go and tap that wall, then the wall barely taps you back. You don't break your hand or your knuckles. But if you give it everything you've got and punch that wall, which doesn't sound smart to me, the wall is going to give the same amount of force back to you, and you're the one who ends up with broken hand. Because for every action, there's an equal and opposite reaction. Another example I gave you was when you go on a field trip to the zoo and you have to walk all through the whole zoo. The monkeys, the outside animals, the reptiles, the birds, the swimming animals, whatever, giraffes, and you walk the whole zoo. Your feet at the end of the day hurt because every time your foot hit the ground hits your foot back. Okay? So here is for every action, there's an equal and opposite reaction. So let's look at this first one here. The fish, the action part is that the fish pushes the water molecules, right? So it can swim through the water. Part 2, or the reaction, is that the water is pushing on the fish. So when you see questions on the test or quiz over Newton's third law of motion, all they're talking about is just that part. They're not talking about anything else. We're not talking about the other fish. We're not talking about Nemo. We're not talking about the seaweed. We're not talking about a shark that's over there. We're talking about this fish and the water that he's touching. That's it. So whatever you talk about over here, which is the fish in the water, on the reaction part, it better be flipped, and it better be the water and the fish. Okay? Let's do it again. Here we go. We've got these people over here, they're boating, right? So the action is the boat pushes on the water.